All right, so hello everyone. Welcome back to your Concrete 35 tutorial. Hope everyone's doing well. So in this tutorial, we'll be talking about everything related to context-free grammars and context-free languages. All right, so context-free grammars, let's jump right into it. Let me just remind you of the definition of a context-free grammar. Like you saw in the lecture, a context-free grammar is like any other grammar G, which has a set of variables, terminals, start variable, and production rules. And what distinguishes a context-free grammar from any other grammar, so how is it different from a regular grammar, is the form of its production rules. So for context-free grammars, the production rules P look like a variable on the left-hand side, and on the right-hand side, any combination of terminals and variables. And so if I have something like S gives me A, S, B, B, then this is an example of a production rule that could be part of a context-free grammar. So now you're probably thinking, oh, well, doesn't that mean that any grammar is context-free? No, not necessarily, because we have the notion of context-sensitive grammars, which you'll see at the end of the course, which look very similar to context-free grammars, except that on the left-hand side, now I can have more than one variable. So something like this would be an example of a production rule for a context-sensitive grammar. So the reason why we call it context-sensitive is because the left-hand side is kind of like your context. So here the context matters, and here the context doesn't matter, so that's why it's context free. Okay. All right, so that's a context-free grammar. Then from a context-free grammar, we can define the notion of a context-free language. So language L is context-free if and only if there exists a context-free grammar G such that the language generated by G is equal to L. Okay. So then two questions here. Are regular languages also context-free languages?
Yes.
Yes, very good, thank you. So yes, they are. Why? Why is this true? Because I can remind you that a language L is regular. We can say if and only if there exists a regular grammar G such that L of G is equal to G, right? But a regular grammar is just a very restricted version of a context-free grammar, because in a regular grammar, you're only allowed to have a single variable, at most one variable at a certain position. In a context-free grammar, you're allowed to have any number of variables on the right-hand side and any combination with terminals. So clearly, yes, all regular languages are also context-free languages. Are context-free languages also regular? This is something that we're going to answer in one of the exercises. All right, so that's quickly a review of what a context-free grammar is. Now let's look at an example of a possible context-free grammar. So we have the following grammar G here, which has this set of production rules. And we want to know what language is generated by the following context-free grammar. So we have two sets of production rules. We have the ones for the variable S and the ones for the variable A. So if we look at the ones for the variable for S, it's ASB. So this is the very famous production rule to give you A and BN, right? So what this tells me is that I'll have initially, when I start my derivation, I have the possibility to have n number of A's and n number of B's on the left and on the right, right? So suppose you generate a few of those. You use a few of those production rules. So let's say you're at the point where you have a cube s b cube. Okay, then at that point you can use this production rule to allow you to switch to the next set of production rules with a. So then I can replace s with a, so I'll have a cube, a b cube, right? And then this set of production rules is also a very famous set of production rules. If you notice here, every time I have, so let me go to the example here. So every time I have a symbol, let's say this is A on the left, then I'll have the exact same symbol on the right, right? So let's say this was A, let's say A1 was A, then I'd have an A at both the left and the right. And then I would have the same thing for the next symbol. So let's say A2 is B. Then at the left, I would have B, and at the right, I would have B. So what's going on here is that I'm essentially writing the same symbol at both the left and right position. So at you can think of it at position 0 and at position, let's say I, where I is the end of your string for that's derived by A, let's say. So that continues, right? So I keep going within my string, and what you can notice is that the string that I'm going to get from A is going to look like something like, say, A, B, A, B, A, which is a string that if you read it forward is going to look like the same thing if you read it backwards. So from left to right and from right to left, the reading of the string is identical. That is, W is equal to W reverse, right? So so that set of production rules, so this set of production rules allows you to do that. And then this extra set of production rules just tells you that you're going to have a string like this, which I'll give it a name, is a palindrome. So a palindrome is a string that read from left to right and from right to left is the same. So this set of production rules with A is going to give you strings that are palindromes, and the fact that your terminals are only A and B means that you're going to have an odd length palindrome. So why is that? Because at each production rule that has a variable, you're going to add two strings, right? You're going to add two strings. And then at the end, you're going to add one extra string, right? So, or symbol. So you have two, let's say, times the number of times you use this set of production rules, plus one extra production rule for A or B. And this is equivalent to the number of symbols in the string that's generated. So then, okay, what does that mean? That means that the string that is generated, the sort of the form or the pattern of the string that's generated by this grammar looks something like AN, BN on the left and the right, V reverse. So that is the same string reversed, and in the middle, either A or B. Okay, so this might be a confusing way to write it. So a better way actually to write this would just be AN, BN, and in the middle W, and then you could write such that W is equal to WR, and the length of W is odd. So that's why it's written like this here, because that's a much clearer way of writing it for a language. Okay, but so the main idea of this example was to show you that in context-free grammars, you don't necessarily have variables always at the same place. You might have terminals that are interchanged with variables, and so you need a new way, a new mentality to tackle what the languages generated by the context-free grammars are. And so deriving it this way and then noticing these two, so noticing these two very important patterns is a way to do that. Okay, so that's for this example. Okay, so now let's see if what I said was clear or not. So I'll give you a minute. What language does the following grammar generate? So I'll give you until 4:27.5. All right, so hopefully you had a little bit of time to look at the grammar, maybe not fully understand what the language was, but to at least understand its logic. So with that being done, let's look at this exercise together. So one of the traps here was the fact that we had these two extra production rules, which in fact are actually useless. So you're gonna see a bit more about useless and sort of useless production rules probably in this lecture, and how to get rid of those in context-free grammars. But for now, what you can just notice is that let's say I start with S, right? Then from my start variable, I have, I can, let's say, replace S with C. Okay, so now I'm replacing S with C. So now I'm stuck with using this production rule. So if I replace C with terminal C, CD, then what's going to happen is I can never get rid of this variable, right? Because I don't have an extra production rule here that gives me just a terminal. So what that means is that I can, no matter how many times I derive a new string, I can never get rid of all my variables. I'm still going to be stuck with a variable C, which means that this production rule isn't useful at all. And by definition, because D is only used by this production rule, I can also get rid of this one too. And sort of by default, it means that I don't really need to think of C here. And so it sort of simplifies my task to just look at these production rules. So this is now the new sort of equivalent context-free grammar that I need to look at, and for which I need to find the language. Okay, so what seems to be the shortest strings accepted by, or generated, excuse me, by the grammar? Well, for sure, I can generate A, right? From S, I can generate A. It doesn't look like I can generate anything smaller. Then let's say instead of replacing S with terminal A, I wanted to do something fancier. So let's say I replaced S with little a, capital A. Then I could, for one, I could replace A with lambda, but that wouldn't really help me. That wouldn't be interesting. It would just give me A again. So the only other interesting thing that I could do is replace A with little a b, right? So with little a b. So then I would be back, I would be at this production rule. So then I need to go back to A by using this production rule. So I would replace variable B with variable A terminal A. And then I can replace, let's say, A with with lambda, so I get a cubed, okay? And so what you're going to notice actually is that if I start at S, right? And so there's two possibilities. Well, there's three possibilities if I start at S. I can go to A, so that's not super interesting. I can go to little a, capital A, and I can go to B. If I go to B, so we already did this pattern. If I go to B instead, then what happens, I replace B with variable a, and then I can, what can I do from there? I can replace it with lambda. That's not very interesting. And the other thing I can do is replace a with ab, right? And the same thing can be said from this production rule, right? So if I started here, so essentially what that means is whenever I'm at A, to get something new, I need to go to B, which means that I'm going to add an extra A and then go back to A, adding another extra A so that I can finalize my string and replace it with a lambda. So that means that I'm going to start my string with an A, right? So I always have at least one A. And then what's going to happen is I'm going to add A's in pairs, right? So I'm going to add A's in pairs, meaning that the language that's generated here, in this case, the language generated by this grammar is, let's say, for instance, if I write it in terms of regular expressions, is the set of strings or the language of strings where you have an odd number of A's, right? So that's one way to sort of notice that this is the language generated by G. It's in the sense that if you start at S, whatever you do to get a final string, you need to interchange between these two. And the fact that you're interchanging means that you're going to add an extra 2 A's every time you're looking for a new string, meaning that you get only strings of odd length because, again, why? Because you're always starting with at least with a single A.
Sure.
Yeah.
I missed something at the very beginning. You said that C and D were useless.
Yeah.
Why would it be useless?
Well, so they're useless in the sense that they can never generate a terminal string. Because, so let's say I start, right? So from this example here, if I start at S and then I replace S with C.
Okay, I understand. C refers to itself continuously.
Yeah, exactly.
Okay, I understand.
Yeah. Yeah, that's one way of saying it. It's infinitely recursive. The way that the textbook refers to this is being a non-generating production. Okay. So there's a question about replacing. That's another. Yeah. So that's another possibility. Is you could sort of that's a good trick actually, is replacing certain variables to help you determine what the language generated by your grammar is. So for example, here someone said you could just say, well, whenever you use a B, you just go back to AA. So then what you could also do is just replace this production rule with AA. So that's a very fair observation, and that would indeed help you simplify your life in the sense that it would sort of clearly show you that you're always adding 2 A's. And the fact that if I did the same thing here, so if I replace this with AA, then you can see that from S, you're always going to start with a single A, and then with A, you're going to add an extra 2 A's. So that's another good observation and another good way of quickly seeing what the language generated by your grammar is. Okay, And then, is drawing a DFA a good strategy to discover the language generated by grammar? Would that be, by grammar, would that be regular or context free? So you can't draw a DFA if the language is not regular, right? And so if you have a context-free grammar G, right, then it's not always immediately obvious that this grammar actually generates a regular language. So here it just so happened that the language was regular, but in general it might not be. And so that means that you won't necessarily have an FA to correspond to your grammar, because FAs are only powerful enough to accept regular languages and not context-free languages. So then, to answer your question, you could really only do that if you were sure that the grammar was regular. Okay. All right. So that's a good question. So now there's a lot of questions about grammar creations, which might take a while. So I might skip one, but we'll see. So this one I'll first do sort of as an example, and then we'll see if we can do the others sort of together. So this was an example of, you're given a context-free grammar and you want to find the language generated by that grammar. This is, of course, the opposite. Is you're given a language and you want to find a grammar G, and in fact you want to find a context-free grammar G such that it generates the language. So in this case, what's my language? It's ANBKCL, where L is equal to 2K plus N. So in other words, the number of C's here is equal to twice the number of B's plus the number of A's. Okay, so how can I write this a grammar that generates this language? So what you need to notice is if you start the string generation with C. So let's say I add a C to my string, then or actually that's not the right way to look at it. You have to look at it sort of the other way with B and A, because the C depends on the number of A's and B's, right? So starting with C would not have been the right strategy, actually. So really what you do need to do is, let's say you generated a B, then what you need to notice is that there must be twice the number of C's as B's, right? So for every B you generate, you need to add 2 C's, okay? And so you can keep doing that, right? You can add, for every B you add 2 C's, sort of, you can keep going. So here I have B3, and so I have C6. And then at some point, this process is going to end, right? So let's say you're satisfied with, let's say, B4, C8. Then you can start adding your A's. So let's say I add an A, then I'm going to add an extra C, right? Because it has to be 1 for 1 for A's. Then again, if I have another A, I have to add another extra C, right? So it's 1 for 1, the number of A's and C's. And for the number of B's and C's, it's, let's say, 1 for 2, right? And so then you just have to kind of observe that pattern and then integrate it or implement it into your context-free grammar. So how do we do that? Well, we can say that if you start at your start variable S, and from S, you generate, say, a B on the left of S, then you have to generate 2 C's on the right of S, right? So you can keep doing that, right? You can keep doing that sort of to get this process. So let's say I get to B4, C8. Then once I'm there, let's say I want to stop doing that. So I stop doing that. And now hopefully someone will realize that this wasn't the right way to generate this this grammar. So the reason why so I made a mistake. And so the reason why I made a mistake is because if you do something like this, then you're sort of forcing yourself to have the B's on the outside and then the C's on the outside. So there's no way for the A's to go back here, basically. Okay, so that was a mistake that I just made. So the strategy is, in fact, to start from the outside, right? To start from the inside and then go inwards, okay? So instead of saying, I'm gonna have a B to the left, so this is gonna come later, basically. So now what I can just say is I can have an A to the left, and for each A, I'm gonna have a C, right? So this is going to take care of the fact that I have n A's to the left, and I have how many? I have 2k C's and then n C's, right? So it's going to deal with this part of the string and this part of the string. And then I can go sort of inwards. So I can say I can use another variable A, and that variable A is going to take care of, for each B, I'm going to add 2 C's. So for each B on the left of A, I'm going to add 2 C's on the right of A. And then that can continue until I get, until I sort of don't want to keep going, and then I can replace A with the empty string. Okay, so hopefully, so sorry about sort of messing up at the beginning, but actually I think that might have been useful just to show you how that could have led to an error. And so is it clear sort of why this generates this language? I'm going to take silence as a yes, even though it's typically not the case. Okay, so I have this grammar. Okay, good. Okay, all right. So I'm glad there's questions then. Yeah, I can. So forget a second about just creating the grammar, and let's just think about a string that belongs to L, right? So strings that belong to L look like AN, BK, and CL, where L is equal to N plus 2K, right? That's what I wrote. Yes. Okay. So in other words, let's say I have NAs, right? I have NAs here, and I have KBs here. Then the number of C's is completely determined by the number of A's and B's. So I have 2KC's here, and then I'll have NC's here, right? So then how do you sort of, what would be one way of, if you just didn't know anything about grammars, of sort of working your way through this kind of string? Well, you could say that for each A that you have on the left, you have exactly 1 C on the right. So that just translates to the production rule. If I start with S, then I can replace S with A. So I have an A on the left, and then I have a C on the right, and then everything in between for now is just S, right? And then I can again replace that by the same production rule. So I can get A, S, C, C, and I can keep going, right? I can keep going until I have, let's say, N A's, and I have N C's. So at that point, once I have N A's and I have N C's, then I can go to the next variable. I can go to the next variable A. And then this variable A is going to take care of, for each B that I have, consider 2 C's, right? So then what's going to happen is I have NAs and NCs, and then for each B that I have, I'm going to add 2 C's, right? Because the number of C's, so this is the number of C's, so the number of C's is 2 times the number of B's. So So then for every B that I have, I need twice as many C's, right? So that keeps going. So then let's say I have KBs. So then I'll have 2KCs. And then at that point, I'm done generating a string that looks like that. So then I can just replace that by lambda. Okay. And so then that's how this translates back to this set of production rules. Okay. So hopefully that's clear. So the idea in general, and so you might see a lot of these examples, or at least you might see them in your assignments. I actually haven't looked at assignment 3, so I'm not entirely sure. But whenever you have something like the number, like when you have a fixed structure like this, and you're just playing with the number of elements, then you're sort of forced to have a structure kind of like this, where you're forcing the sort of correspondence between the number of C's and number of A's, or whatever number of B's and number of C's. Okay, so so that's for, let's say, this exercise. Now let's see if this was understood with another exercise. So I'll let you try this one. It's pretty close to the same idea as before. So I'll give you maybe a minute, and then we'll look at it together. Okay, so looks like someone has seen how it's similar to the previous exercise. Well, it's not exactly the same, but it's going to have a similar flair. The only thing that might be sort of tripping you up here is the fact that you have a minus. And fair enough, it's difficult to sort of, minuses in general are pretty abstract. And so what you can do is you can just say, okay, I know that m minus n is equal to 1, but what does that really mean? That just means that m is equal to n plus 1. Okay, so what does that mean? That means that if I have a string an bm, then really I have a string an bn plus 1. So really what that means is I have, for each a, I have a b, right? So there's this one-to-one correspondence. And then, so I have, let's say, n a's and b's. And then at the end, I have an extra b, right? So that's one way to think of it. Another way to think of it is what René did is start with the extra b. So you could also start with the extra b. Let's say it's at the right. So let's say I have an extra b. This is a +1. And then I have a 1-for-1 for a and b, right? So so that's this solution, right? That's, let's say I have the extra b is at the rightmost, right? So I have ab. Then I do the rest as just for each a, I have a b, right? So for each a, I have a b, and then at some points I just stop, right? So the other way that I described could have been you have s is replaced by, let's say, ASB, right? And then at some point, you can just say, all right, well, let me just replace S with B. So this would be, I guess, a maybe simplified version if you want. Although this grammar is just as good as this one, right? What is maybe not equivalent is what someone else wrote is this grammar. So this isn't quite the same as this. And the reason for that is because here what you're saying is that for each A, you have two Bs, right? So let's say I have 3 A's, then that means I'll have 6 B's. So this is actually a very nice context-free grammar, but it's the context-free grammar G for which L of G is A, N, B, M, such that M is equal to 2N, right? So for each, so there are twice as many B's as there, or sorry, there are 2 times the number of A's. So 2 times the number of A's, that's equal to the number of B's. Okay, so I wanted to say it in a fancy way, but that's another way of saying it, right? Because for each A, you have 2 B's. Okay, so but it's a good try, and it's good to make sure that you understand the differences between let's say this grammar and this grammar. Okay. All right. So any questions about this before we go to the next one? No. Okay. All right. So the next one is a bit different. This is another kind of standard context-free grammar exercise that you might see. So yeah, I'll give you maybe, let me give you a minute. I'll give you another minute to try it. See what you come up with. Okay. So so let's see how we can create a CFG here. So what does a string here look like? So it looks like a string U, which has length 2, which has to be at the beginning and at the end, right? So I know that since my string U has length exactly 2, U is either AA, AB, BA, or BB. So that means that any string, let's say I have a string, I don't want to use W, let's say I have a string T in L, right? Then T has to look like either AA, and then something, AB, AB, and then something in the middle, BA, something in the middle, BA, or BB, something in the middle, BB, right? So you can kind of see that there's kind of ors here. So maybe let's already start by the start variable s. Okay, so I have my start variable s, and let's deal with the next part in another variable. We don't need to do it this way, but let's see if it'll help us understand. So this is for the start variable, then I go to the next variable. The next variable is there to handle what? It's there to handle this part of the string, right? The VRWV. So VRWV, right? Like I said before, it's one of the classic string patterns that you see for context-free grammars. It's the one where you put the same symbol at the leftmost and at the rightmost part of the variable, right? So so in other words, it's kind of like you have a palindrome. So here you have a palindrome, but in between it, you have a string of length 3 in this case, right? So I can create, this is how I can create the palindrome, right? So suppose I'm here, right? So I start at S. Let's say I use this derivation rule. So I have A. Then let's say I wanna start creating or writing my palindrome. So let's say I use these two production rules a couple of times. Let's say I create ABA on the left and ABA on the right. Then suppose I'm done, I've finished creating my sort of palindrome. Then the only thing that's left here is the string of length 3W. So then at that point, I can go to, let's say, another variable B, and B is going to take care of my string of length 3. So I can either be, so let's not brute force it, let's be slightly clever. Let's say B points to C, 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 and then C is replaced by A or B. So then each of these has two possibilities. So then, right, so 2 times 2 times 2, I have 2 cube possibilities. And of course, that covers all of the possibilities. So all of the strings of length 3. So this is just to convince you that doing this is the same as sort of brute forcing it and writing all of the strings individually, okay? So then that means that this is the final grammar that would generate a string, any string that belongs to sort of this language. Okay. So maybe one comment about this actually is, let's say I wanted to be even more, like I wanted to save even more space, and I had used something like S gives me CC ACC. Then would this have been sort of equivalent to writing AA, and so on? What do we think?
Yeah, I think so.
You think so? So is the fact that you have the same variable a couple of times, does that sort of obligate each of these variables to be replaced by the same terminal?
No.
No, right. So then what I'm trying to get at is, then if you did something like this, right, then you could say, oh, well, I can replace this C by A. Let's say I can replace this C by A, but then I can maybe replace this one by B and then this one by B, right?
Oh yeah, true.
Right. So that's something to maybe be careful about, is that the same variable at the same the same variable many times in the same production rule doesn't mean that it's going to generate the same thing, right? So that's something to be, what's the word? Cautious of. Yeah, there you go.
Sir,
Yes.
for the U component of the language that has a length of 2,
Yes.
you said that we have like 4 combinations, AA, AB,
Yes.
BA, BB.
Yes.
But in this example, you have them mirrored. So you have AA, AB, AB. But couldn't we conceivably have like AA, BA, and that would still be valid?
Well, I'm not quite sure I understood, because if you have any string, suppose you have a string, let's say string 1 that was in L, then it has to start with U.
Oh, it's the same U.
Yeah, it's the same U.
I understand.
Yeah.
Okay, I understand. I'm sorry.
No worries. No, nothing to be sorry about. That's a good question. Oh yeah, that's another excellent question. So the other excellent question is let's say I hadn't forced you to be 2. So let's say there wasn't a restriction on 2, and I just said you have to have the same variable at the beginning, or sorry, not the same variable, the same string at the beginning and at the end. So that's an excellent question. And it turns out that if you no longer have this sort of finite restriction and you can be as long as you want, then actually this is no longer context free. So the fact that you have sort of, so what I mean by that is, if I have, let's say, the language UAU, such that U is in AB star, then this is already too much for a context-free grammar to handle. This is actually not context-free. So that's a very good question. And so you're going to see why this is not context-free when you look at the pumping lemma for context-free languages. So there's a second pumping lemma. I'm sure you're very happy to hear that. That disproves that a language is context-free. And so if you apply it to this example, you would be able to show that this is not context-free. And in fact, you need something even more powerful than a context-free grammar to generate this. Okay, so, but that's a very good question. Yeah. All right, so last exercise here for creating a context-free grammar. Again, you can maybe, yeah. So I think this one is also fair for you to try. So try it out, and we'll look at it together. All right, very good. So yeah, I'm happy someone. So that's actually pretty impressive. That was kind of less than a minute. So let's look at the this question together. Basically, from what actually René wrote in the chat, you can maybe think already what the sort of structure of any string in L would look like, right? Well, I mean, the structure is here, but maybe just to emphasize it even more, it's basically any string, right? Any string U, and then any string W. It doesn't matter if U and W are not the same, or if they're the same. They just have to have the same length, right? So for instance, I could have, I don't know, A, B, A, B, and here I could have B, 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 A, B, B, right? I could have something like that. So I have this part of the string and then this part of the string, and then I have just a single A in the middle. and I have a B on the right-hand side. So then what you could do is, because it's difficult, right? You can't really start by generating this part because you need a way of keeping track of the number of elements here and making sure that they match the number of elements here. So really what you need to do is you need to kind of do these two things together and then add or sort of append an extra B. So that's essentially the idea behind a first reduction rule that would say just like, let's say the variable A is going to handle this. So the variable A is going to handle this. And then at the end, once the variable A handles all that stuff, so in other words, the UAW, then I can add a B to that, right? And then from my A, so my A, what does my A need to do? It just needs to give me the same number of symbols or elements on the left and on the right of A, right? So whenever I'm producing from A, I just want that I want that the number of elements on the left equals the number of elements on the right. So let's say I have 3 elements here, then I have to have 3 elements here. So what that means is that every time I produce one element here, I need to produce another element here. So it doesn't matter if this is A and this is B, right? It doesn't matter if they match or they don't match. They just need to sort of be there, right? So then the idea is, well, now I'm going to use that sort of trick. I'm going to say, let's say B gives me a single element, A or B. Then every time I'm going to use A, I'm going to replace A by an element on the left, an element on the right, and then A. So this ensures that I always have the same number of elements on the left and on the right of A. And then at the very end, I can end this process by replacing the capital A, so the middle, by terminal A. And that would be the context-free grammar to generate this language. Okay? So, all right. So any questions about this? I don't think so. Or, I mean, I don't know what I think. You have to tell me if there are questions, but it doesn't look like there are. So maybe just I wanted to, yes? Oh, no, okay. I heard someone unmute themselves. Yeah, so maybe I just wanted to say something about one of the first, so let's actually look at this one. Yeah, so let's look at this one. So here, I gave a context-free grammar to generate this language, right? So do you think it would have been possible to generate this language with a regular grammar? So would a regular grammar be able to generate this language? Everyone's thinking no in their heads, and they're just not typing in the chat, right? Because yes, very good. The answer is no, right? Why is the answer no? Because this is an bn plus 1, right? So very similar to an bn. We proved by the pumping lemma that this was not regular. And so similarly, we can prove, let's say if I used as my string am bm plus 1, if I use this as my string, then I could derive a contradiction and show that this language is also not regular. Okay, so you're probably thinking, all right, Ches, so why do we care about this? Well, the reason why I want to show you this is because what this example implies is that let's say this is a set of regular grammars. So this is the set of regular grammars. So let's say LA star, ANBM, for n m greater or equal to 0. So let's say I have these languages. Then around those languages, I have the set of context-free languages. Then what this shows is that I have at least one language L that is in the set, or that is in the set of context-free languages, and that isn't in the set of regular languages. And so what that means is that the set of regular languages is a proper subset of the set of context-free languages. All right, so that's what that means. And that's important to keep in mind for the sort of remainder of, I would say, the course. Okay. All right. So yeah, so I don't think, yeah, I think what might be better is, because I need to mark your assignments. So, and I would like to do that by the end of the night. So I think what I'll do is I'll stop here and I'll post a recording on derivation order and ambiguity. Maybe just very high level, derivation order is just the order in which you replace variables. So just a reminder, a leftmost derivation is when you keep replacing the leftmost variable, and a rightmost derivation is when you keep replacing the rightmost variable. And then ambiguity is directly related to, so it's directly related to derivation order, in the sense that if you have a string W in a language, and there are two leftmost derivations, so there are two ways in which you can leftmost derive a string, then that means that that grammar is ambiguous. The grammar that, the language that generates the grammar, or sorry, the grammar that generates the language, if a string in that language can be derived in two or more ways by a leftmost derivation, so two or more leftmost derivations, or two or more rightmost derivations, then that's an ambiguous grammar. Okay. And then if a language, so then if a language L cannot be generated by a non-ambiguous grammar, so there does not exist an unambiguous grammar that generates it, then that language is inherently ambiguous. Okay, but I'll post a recording in case you want a sort of a deeper dive in this topic. But this is just, that was just kind of a high level summary of what inherently ambiguous and ambiguous those concepts mean. Okay. All right. So then I don't know if there are any questions in general, or about the assignment or anything else. No? Okay. When using pumping lemma, can we pick a certain number? No. So no, we cannot do that. So that's, if you look at my if you look at the lecture, the tutorial slides, you can never set a particular value for m. So m always needs to be arbitrary. So it can be something like m cubed or 2m or m plus 1, but m cannot be a fixed number, because then what you're doing is you're just showing a contradiction for a particular m, which doesn't give you a contradiction for all possible cases. So then that wouldn't be a correct usage of the pumping lemma. Okay, but good question. Any other questions? So I'll wait maybe a minute. Yeah, no, so it doesn't seem like it. So, all right. So like I said, I'll post an extra recording on ambiguity and inherently ambiguous languages. And I will go back to marking your assignments now so that you can get the marks for that by this evening. All right. So, so I guess that's it. So have a nice lecture, everyone. And I will see you Monday. All right. Take care, everyone. Bye-bye.